Sounds good. Well, good morning, everyone. I really appreciate everybody participating in this defense. I'm thrilled to have you here. I'm Elizabeth Heiss, and I've had the pleasure of advising Wes Franklin during his master's thesis. Today, he's going to do his defense, and we're going to learn about microplastics in the environment and in the Resacas systems around Brownsville. After Wes completes his defense, we're going to have a time period where the general audience can ask Wes questions, and then we're going to excuse ourselves and have the committee have a meeting and a private conversation with Wes. So if everyone will stay muted, then we won't have any background noise coming in from other places. So Wes, take it away.
All right, I'm going to go ahead and share my screen. Can y'all see my screen? All right, I'm going to take that as a yes.
Yes, I can.
Sounds good. Okay. Well, first off, I would just like to welcome my friends and family. I would like to welcome my committee. Thank y'all for all taking time out of your day to come listen to my thesis defense. I hope that y'all learned something and enjoy this talk as much as you can enjoy a scientific talk. So I'm going to go ahead and get started. The name of my thesis is an assessment of microplastics, an assessment of microplastic pollution in the fish, sediment, and water of Resacas in the lower Rio Grande Valley, South Texas. My advisor is Dr. Elizabeth Heiss, and my committee members are Dr. Jude Benavides and Dr. Alejandro Fierro Cabo. So there have been no studies done in the Resacas of the Rio Grande Valley involving microplastic pollution. So we had several goals coming into this study. First was to provide novel information and data on the microplastics in the Resacas. Second was to record where microplastics are found in the environment, to compare the amount of microplastics found in different species of fish, to document the different structures of microplastics, so things such as microfibers, chunks, films, and foams, and to find out which of these structures were most prevalent in our Resacas. And lastly, we wanted to characterize the composition of the microplastics, so things such as polyethylene terephthalate, polyvinyl chloride, and polystyrene are a few compositions we could have in the Resacas. So if you don't know what a Resaca is, it's a local term. So Resacas are defined as ancient distributaries of a river, in this case, the Rio Grande River. They used to function as distributaries of the Rio Grande, carrying fresh water into the Laguna Madre and the Gulf of Mexico. Many Resacas used to function as seasonal water bodies that would dry up in the dry season and become inundated during the rainy season. Because of human impacts, they usually stay inundated year round as we use them for municipal water storage. These bodies of water are very important to the wildlife and aquatic species here, as they're some of the only freshwater sources in the valley. So we're in a very saltwater dominated area. We have the Gulf of Mexico, we have the Laguna Madre, which is a hypersaline lagoon, and then we have different salt lakes such as Sal del Rey and things like that. So there's only a few freshwater bodies here. We have the Rio Grande, we have the Arroyo Colorado, and we have the Resacas spread out through the valley. So these bodies, like I said earlier, primarily serve as municipal water storage. They also serve as stormwater runoff canals and irrigation water storage for different agricultural purposes. Naturally, they function as habitat for many species of migratory birds and other aquatic species such as fish, turtles, and amphibians. And because of their setting in urban areas, it's worried that they could become sinks for pollution. So microplastic pollution as well as different chemical pollutions. So if you have a large congregation of these microplastics being stuck in these pools, this is going to affect the water quality, and it's going to affect the organisms as well, which will in turn affect humans because we rely on these Resacas. So this is a Google Earth satellite image. It shows the city of Brownsville as well as some surrounding areas, and it shows our 11 Resaca pools as well. So at the bottom, we have Lozano Banco. There was only one pool in the system, and this is actually an oxbow lake. So this was the only pool in the Lozano Banco system. Next, we have the town Resaca system. There's two pools here, TR05 and TR14. Next, we have Resaca de la Guerra, and there were 4 Resaca pools here, RG31, RG39, RG42, and 43. And then lastly, and on the outskirts of Brownsville, the most rural Resaca is Rancho Viejo, and there's 4 pools here as well, RV 56 and 54, RV 68, and RV 85. So switching from Resacas to microplastics, this is the next key part of our study. Microplastics are any plastic particle that's smaller than 5 millimeters in length. There's 2 criteria here. We have primary microplastics, which are those that are manufactured to be very small, very minute. So things like nurdles that make larger plastics, things like microbeads that are found in cosmetics and toothpaste and abrasives. And then we also have secondary microplastics. Secondary microplastics are more prevalent in the environment, and they're your plastics that come from the degradation and breakdown of larger plastics from things like wave action, UV radiation, chemical breakdown, things like that. But they're going to be your most prevalent microplastic. Among these two categories of primary and secondary, they can further be specified into foams, pellets, fibers, films, and fragments. And it's now known that microplastics have invaded many, if not all, aquatic environments. They're nearly everywhere. So here's an example of two microfibers that were found in our gizzard shad samples. On top is a green microfiber. On the bottom is a red microfiber. And these are just come from the breakdown of larger plastic fibers. So a little bit about the negative effects. So many aquatic organisms, including turtles, seabirds, fish, whales, a lot of aquatic organisms have been found with microplastics in their digestive tracts. These can get here many ways. One of the ways that they can get here is by fish ingesting other organisms with microplastics present in them. Another way, fish can just ingest water or be picking up food from the sediment and get these microplastics in their system. And another way, fish can actually mistake these microplastics for food items, the same way that a sea turtle would mistake a grocery bag for a jellyfish or something like that. They can mistake microplastics for things like zooplankton and phytoplankton. So whenever microplastics are passed up through the trophic levels, this is known as biomagnification, and this is a very serious matter. So it's basically whenever pollution it congregates at higher levels and higher trophic levels. So let's say you have a microscopic organism with one plastic, you have a small fish that eats 10 of these microscopic organisms, so it'll have 10 plastics, and then you have a larger fish that will come along and eat 10 of these smaller fish. So over time, you'll have the buildup of microplastics and the chemicals associated with them in higher trophic levels. And these can leach into the tissues of these higher trophic level organisms, which are usually game fish, and they can have toxic effects on both the organisms and the humans that eat them. And this is an example of one of a blue microfiber found in the stomach of one of our gizzard shad. So not only chemical effects, there's also physical effects that these have on animals. So these things can become tangled in and they can clog up the digestive tracts of animals. This leads to lower rate of consumption. It also leads to false fullness. False fullness is basically what it says. They have these plastics in their stomachs and the fish will think that it's actually food items. So because they have this weight here, they won't be eating as much. They'll have lower rates of energy. And in serious cases of blockage and entanglement, it can lead to starvation. Other effects of microplastics include inhibited growth and development, oxidative stress, loss of energy, endocrine and neurotransmission dysfunction, and also genotoxicity. And this can lead to, this happens whenever the chemicals from these microplastics can actually negatively affect the genomes of these organisms. The effects of these microplastics ultimately lower the reproductive capability and the fitness of all organisms associated. And it's important for us because it's going to be affecting these higher trophic level organisms. And as humans, we are higher trophic level organisms, so we could be getting these effects as well. So that's to do with microplastics and Resacas. These are the real stars of this study, I guess. Without them, we wouldn't have had it. On the left, we have what's called Terrygoplichthy's Disjunctivist. It's also known as a sailfin catfish. Don't worry, I'm going to be using the common names just for simplicity purposes. So this catfish is a benthic forager, and that just means that it feeds on the bottoms of the Resacas. It's also an invasive species. It's native to the Amazon basin, so it shouldn't be here. It has negative effects on our environments. It competes with native species for food sources. It contributes to higher rates of erosions and things like that. So that is our sailfin catfish. And on the right, we have Dorosoma cepidinum, also known as gizzard shad. This is an important forage fish, and it's also an important food source for different species of game fish, largemouth bass, striped bass, different types of gars as well. So I caught these species in the 3 different Resaca systems that I mentioned earlier: Resaca de la Guerra, Rancho Viejo, the town Resaca system, as well as Lozano Banco. I obtained 49 sailfin catfish and 70 gizzard shad. I obtained 3 sediment samples from each pool, 2 benthic and 1 shore sample, so 33 in total. And I obtained 2 water samples from each pool, 22 in total. So for my methodology, this is just going to explain how the fish were caught, how the sediment and water samples were analyzed, and what we did past that. So for fish, we caught fish using gill nets and cast nets. So this is an example of a gill net, and as the name implies, these fish will swim into this net, get caught up by their gills and their fins, and they'll be stuck there until we release them. For these fish, once they were captured, we would bring them onto the boat. We would identify them down to species. We would measure them. And then for the native species, we would release them besides our gizzard shad. And for the invasive species, besides our sailfin catfish, we would have to terminate once we got back to the shore because you can't release invasive species back into the environment. For our gill nets, we would deploy them for 30 minutes, 2 times at each location. We chose 30-minute intervals because we figured this was ample time to catch these fish, and we also wanted to limit our non-fish bycatch. So things like diving birds and turtles will become captured in these nets, and if you don't get them out in time, they will end up dying. So we wanted to limit that mortality rate. So once we caught our target species, we would take them back to the lab. We would separate their digestive tract from their bodies. So this is a gizzard shad. You can see the body cavity here, and the digestive tract is next to my index finger. So we would remove the digestive tract out of the individual. We would put it into a separate petri dish, and from there we would search the contents of that petri dish for plastic particles. So this light blue piece is an example of a plastic particle right here. So that was for our fish samples. For our water samples, we would take water samples twice from each location at a meter depth. We'd bring them back to the lab and we would pass them through 125 and 63 micron sieves to catch the microplastics. So these gold bars right here are the mesh of one of our metal sieves, and these filaments right here, these red, black, and transparent filaments, those are our microfibers that we were looking for. So that was for our water samples. For our sediment samples, we would capture them using a box core for the benthic layers and a hand shovel for the shore samples. We brought them back to the lab and we put them in a sieve complex like this. It goes from 4mm mesh all the way down to 63 microns, just so we can catch all of the microplastic particles. Once we put it in the sieve complex, we would then put the sieve complex into a shaker system, and this would just shake the sediments for 10 minutes, and it would allow each particle to fall down to its respective layer. From there, we would search each sieve and look for microplastics like this. So that's what our sediment samples would look like. From there, we would identify all the plastic particles as either fiber, chunk, or other. We would photograph them, and then we would move plastics that were large enough to a different lab to be analyzed by Ftir. So Ftir, also known as Fourier transform infrared spectrometry, it's basically a big word for you shoot an infrared light at a plastic particle and it tells you what it is. It's used to identify many different chemicals, plastic molecules, and things like that. And you shoot this infrared beam of light at your plastic particle, and some of this light will get transmitted, some of this light will get absorbed. And based on what is absorbed and transmitted, the Ftir will put this on a wavelength versus amplitude graph, and it'll give you a spectra. And this spectra is basically like a fingerprint for the plastic. And then you can compare this spectra to different other known plastics to determine what your microplastic or macroplastic is. Many Ftirs come with complementary libraries, which will identify your samples for you. This Perkin-Elmer Frontier, it did come with complementary libraries, but it was mainly for chemical composition identification, not really for polymer and plastic identification. So I decided to build my own library. I did this by getting 23 different types of materials. They ranged the plastic resin codes 1 through 6. So we had polyethylene terephthalate, high density polyethylene, polyvinyl chloride, low density polyethylene, polypropylene, and polystyrene, as well as different polyester nylon blends, different type of cotton spandex blends, and different nylon ropes. And we gathered all of these, we uploaded them into the Ftir so that we would have a base library to compare our microplastics to. So this figure right here, don't let it intimidate you. It's kind of complicated, but I'm going to break it down and explain it. This is an Ftir analysis display from one of our plastic chunks from a gizzard shad individual from Lozano Banco. So on the top left, we have the sample name, and under that, you have your unknown microplastic. So you see LB002 chunk. So that's going to be a chunk of microplastic from Lozano Banco, and that's going to be your unknown. In the box on the top right, where this next blue arrow popped up, we have a search score and a search reference. So this search score is going to compare your unknown plastic to a known microplastic, and it's going to give you an accuracy hit. So a score of 0.962, that's a 96.2% accuracy hit. So that lets us know that this microplastic is actually a polypropylene plastic. We also have another analysis we run for even more confidence, and this is a spectral comparison. So on the bottom in the lime green, we have a polypropylene sample. And on the top in the red, we have our unknown plastic. So you can see how close these match up. They're basically like fingerprints, and you're able to tell what is what by looking at this spectra. Also for polypropylene, right after the 3000 centimeter wavelength mark, you had these 4 distinct spikes, and that's how you're able to tell it's polypropylene. You'll see later how we can compare this to other spectra, and you're able to tell these plastics apart. So this is the polypropylene sample. The next sample we're going to look at is a polyethylene. So this is different from the last sample. You can see it has a 97.3% search score hit with one of our polyethylene samples. And on the bottom, our unknown plastic is on top in blue, and our known plastic is on bottom in black. And you're able to see how this is different from the polypropylene. So polyethylene is going to have 2 very steep, very distinct spikes right past the 3000 centimeter wavelength mark. So because of that, and because of the high accuracy score, we're able to tell this is polyethylene. Any search score over 90% is a very confident search score that you can rely on. And then lastly, we have a polyethylene terephthalate sample. So this one has a 92.7% search score, and it also has a matching spectral analysis. For polyethylene terephthalate, you have this unique fingerprint right after the 1700 centimeter wavelength that's able to tell you that it's polyethylene. So those are the 3 types of plastics we had. I wanted to show you an example of each. And to go back, FTIR was conducted on all of our micro and macroplastic samples. We ran over 210 different plastic samples through FTIR. Of those, only 34 came back with identifiable search scores and spectra. 18 were from gizzard shad, 7 were from sailfin catfish, and 9 were from sediment samples. There were no identifiable search scores from our water samples. There's a couple reasons for this. We think that the reason we only had 34 come back with positive or valuable hits is because we are dealing with microplastics here. So some of them are just most likely not large enough to register in the FTIR to produce valuable search scores and spectra. Also, we only use 23 plastics in our library, so it's likely that it's not representative of every plastic in the environment. So we could have just missed some plastics. So that's likely as well. But the plastics identified by FTIR included polypropylene, polyethylene terephthalate, and polyethylene. 13 were polypropylene, 10 were polyethylene terephthalate, and 10 were polyethylene. So moving from FTIR to our just regular plastic results. So this is our results for Dorsum acebedionum, our gizzard shad. So 70 gizzard shad individuals were collected from the 11 pools. 60 of these 70 had at least one microplastic in their GI tract. So 88% of them had microplastics present. 108 plastic pieces were found in these 60 individuals. 77 were microfibers, 25 were chunks, and 6 were considered others. Lozano Banco had the highest number of microplastics of the 11 pools. So you can see here, this blue arrow shows Lozano Banco. Lozano Banco had the most, followed by TR14. Also, you can see in this graph, the blue columns are going to be microfibers, the orange columns are going to be chunks, and then the gray are going to be other microplastics. So Lozano Banco was the highest, followed by TR14. Also, there were more polypropylene plastics found in gizzard shad than any other type of plastic. So continuing on this, we also found that there is a significant correlation between the weight of gizzard shad and the number of microplastics found. And there was also a significant correlation between the length of gizzard shad and the amount of plastics found. So this is very logical. It basically says that the larger the fish is, the more microplastics are found in there. That's what we found. And this graph to the left shows that. It shows weight on the x-axis and the number of microplastic pieces on the y-axis. So you can see this data point, this outlier is Lozano Banco, and it shows how much larger Lozano Banco individuals were and how many more microplastics they had. I left this data point in here. It's clearly an outlier. I left it in here just to show how extreme Lozano Banco was. I also took this data point out and ran a similar simulation and got a high R-squared score that still showed significant positive correlation between weight and the amount of plastics present. So the larger the fish, the more microplastics are present. So for our sailfin catfish, there were 49 sailfin cats caught in all of our systems. 21 of these had at least one microplastic present, so a 43% microplastic present score. This is significantly lower than our gizzard shad. Our gizzard shad had microplastics present in 88% of their individuals. 19 of the plastics found were microfibers, 5 were chunks, and 3 were considered others. So you can see here that TR14 has the most microplastics present, and gizzard shad LB002 had the most, and this one TR14 has the most. There was also a significant correlation between the weight of sailfin catfish as well as the length and the amount of microplastics found. the same as there was with gizzard shad. So as we see, larger fish have more microplastics present in their digestive tracts. Microfibers were also the most common microplastic found here. The graph to the left shows that 65% of the microplastics found were considered microfibers. The town Resaca had the heaviest cellfin catfish of any system, and there were more polyethylene plastics present than any other microplastic. So switching to our sediment results, we've looked at both species of fish. Now we're going to sediment. The microplastic presence average here was 91%. So 91% of all sediment samples had microplastics present. There were 51 microplastics total. 26 were fibers, 9 were chunks, and 16 were considered other microplastics. So this is slightly different from our other parameters. In the fish, we saw that it went from microfibers to chunks to others. In the sediment, it goes from microfibers to others to chunks. Microfibers are still the most common though, so that's a common theme. Lozano Banco also had the highest number of microplastics here, followed by TR05. So we're starting to see that is a pattern as well. Lozano Banco having the most, being followed by the town Resaca system. 14 of the plastics here were large enough to be considered macroplastics. Macroplastics are just simply plastics that are larger than 5 millimeters in length. And the largest microplastic here was 15.4 centimeters. So for a microplastic study, that is extremely large. And sediments had the largest amount of macroplastics of any parameter. There are also more polyethylene terephthalate plastics here than any other type of plastic. And the graph to the left, everything is laid out the same. The blue is going to be your fibers, the orange is going to be your chunks, and the gray is going to be your other microplastics. For water results, the average amount of microplastics here was 88% in all samples. 32 microplastics were found in the water, and 31 of these 32 were fibers. So you can see in this graph that the blue is going to be your fibers, the orange is going to be your chunks. It was predominantly microfibers more than anything else. Lozano Banco had the most microplastics present, followed by Resaca de la Guera. So that's slightly different from our other systems. It usually goes from Lozano Banco to TR, but this time it's going from Lozano Banco to Resaca de la Guera. So for the water results, there were mainly microfibers. Lozano Banco had the most, followed by Resaca de la Guera. And I put this graph in here just to show the breakdown of microplastic pieces by pool. So this shows which pool is most polluted. We see that your blue is going to be your gizzard shad, orange is your cellfin catfish, gray is sediment, and yellow is water. So that shows those for each location. But we see that the most polluted pool is Lozano Banco, followed by the town Resaca pools. Third is going to be our Resaca de la Guera pools. And lastly is Rancho Viejo pools. So Lozano Banco is the most polluted, and Rancho Viejo is the least polluted. So now we've looked at every species, we looked at every parameter. Now we're going to put this in context as it relates to each system. So for Lozano Banco had the heaviest and longest gizzard shad of any system. It had the highest microplastic presence and number of microplastics of gizzard shad for any pool. It had the most plastics by far. Microfibers were the most common microplastic found in all samples. There are more polypropylene plastics than any other type of plastic. And Lozano Banco is located in the middle of the UTRGV Brownsville campus. It's also located next to downtown Brownsville, which could be contributing to the pollution it experiences. Next, we have the town Resaca system. This system had the heaviest cellfin catfish of any system. It was the second most polluted, and microfibers were the most common plastics found here as well. So we're seeing that's a trend that microfibers are the most common. There are more polyethylene plastics here than any other. Town Resaca runs through downtown Brownsville. It's located next to Dean Porter Park, Gladys Porter Zoo, residential housing, and many different roadways, which could be contributing to the pollution it experiences. Resaca de la Guera was our third most polluted. It had the lowest microplastic percentage presence and number of microplastics per individual for cellfin catfish. Microfibers are the most common plastic found in this system as well. There were more polyethylene terephthalate plastics here than any other plastic. And this system is surrounded by residential housing and roadways as well, but it also has some wild habitat and riparian vegetation along these resacas that contributes to its wildness. Rancho Viejo. So this system was the least polluted. It was the most rural. We saw that microfibers were still the most common plastic found in this system. There was only one plastic identified by FTIR, and it was a polyethylene terephthalate. Only 3 cellfin catfish were found in all 4 pools of Rancho Viejo. So this is a very good sign because these are invasive individuals. So the less of them that are there, the healthier the ecosystem will be. And yeah, so this was the least polluted, the most rural system. It was surrounded by agricultural fields, wild habitat, riparian vegetation, as well as some housing. So with that, our conclusions, what to take away from this study. If we were to do this study again, we would find that plastics are most likely to be found in the water, followed by the sediment, then in your species of fish. They're more likely to be found in gizzard shad than sailfin catfish. So when you think of how water is a vector for pollution, how it transports all pollution, it's most likely that the plastics are going to be found in the water and the sediment. Once they get to the pools, they're either going to stay suspended in the water column or they're going to settle out into the sediment, and it would be least likely that they'd be found in your species of fish. We also found that higher number of plastics are more likely to be in the sediment, followed by gizzard shad, the water, and then sailfin catfish. Another conclusion, plastics were found in higher numbers in our more urban Resacas. So we saw that Lozano Banco had the most, followed by town Resacas, and these were very urban. And then Rancho Viejo, which was it was very away from the urban part of Brownsville. It's more rural. These were less likely to have more microplastics present. We also found that plastics were present in larger fish. So a higher amount of microplastics are going to be present in your larger fish. Polypropylene, polyethylene, and polyethylene terephthalate were the plastics found in these systems. There were no polystyrene or polyvinyl chloride plastics found. So that's very interesting. Microfibers were the most prevalent plastic type found in all Resacas and all parameters. We saw that through this whole study. Sources of pollution could include wastewater treatment facilities, recreational fishing pollution, and trash pollution. This isn't an exhaustive list. This is just where some of this pollution could be coming from. And our research definitely adds substance to the scientific literature involving plastic pollution. It's one of the few studies in South Texas to assess microplastic pollution in the environment. And it's the only study in South Texas that I could find that assesses microplastic pollution in freshwater environments. So I do think that the research we did here is very important. And I hope that this catalyzes some more research and some awareness of microplastic pollution in South Texas. So with that, I would like to thank everybody who came and listened to my thesis today. I would like to also thank my advisor, Dr. Elizabeth Heiss, for going above and beyond and helping me with my thesis. Dr. Alejandro Fierro and Dr. Jude Benavides, thank y'all for guiding me into my thesis, giving me advice, things like that. Dr. Sintra, thank you so much for your help with our permits. That was a lifesaver, literally. Dr. Parsons, I would like to thank you for your help with FTIR analysis. Shelby Bissett, I'm in the Coastal Studies Lab right now, so thank you for letting me present here. Thank you for letting me use the microscopes and tools for dissections over here. And David Lacusi, dude, thank you so much for your help in these Resacas, going out there with me for 8 hours a day, catching these huge fish. And it was a lot of fun. It was a lot of hard work, but I had some of the best experiences in the valley out there. So I want to thank you for that. And with that, if there are any questions, I'm going to turn it back over to Dr. Elizabeth Heiss, and she'll let y'all know what y'all can do with questions.
Everybody's muted, so you can't hear the clapping, but I'm sure it's happening. Okay, does anyone have any questions? If you do, you can either put it in the chat or you can just unmute yourself and ask your question. Now's the time to play Stump Wes.
Since we're playing Stump Wes, I'm gonna go ahead and ask my question. The gizzard shad and the sailfin catfish, is there a reason why you chose those two species for your research that you did?
Yeah, so that's a good question. So we wanted to get a representative sample of like where different species of fish feed. So your sailfin catfish are going to be feeding in benthic environments, so on the bottom, and your gizzard shad are more likely to be feeding on the surface and in the water column. So we wanted to see if there was going to be a difference in microplastics in the sediment versus in the water column. So we thought these were good representative species. Also, it was kind of about how likely we were to get permits for these. So sailfin catfish are invasive species, so they really don't have any rights. You're supposed to kill them if you see them, so it's easy to get research permits for those. And for our gizzard shad, it's easier to get permits for those than, let's say, a game fish such as bass or sunfish or things like that.
Nice, nice.
I have a question. When did Matthew McConaughey join our program?
Oh my gosh. Thank you for saying that, Dr. Jude. We mess with him about that all the time.
Every few minutes, I've been looking over to the right, and the mannerisms and somewhat the look, I keep over. And I was like, I had to take a picture and send it to my wife. She started laughing too. Sorry, I'd like to just lighten the mood a little bit here with that little jump before I jump into my serious questions.
No, that's awesome.
My role here, I mean, as I was advising you early on, and of course, I think the level of that advisement kind of dropped off just a bit, obviously, like a lot of other things because of the pandemic. But I was very curious. First off, excellent work. I think your methodology and the structure of your overall approach to this was excellent. And I'm always a fan, particularly when we don't have a lot of established studies already done. I'm a fan of getting it done quickly and early first, and then trying to figure out, what were some of the potential statistical and methodology missteps afterwards, because we need to get some baseline data. So I think it's very interesting that your fish and sediment, and you highlighted this during your presentation, your fish sample and your sediment sample showed Lozano Banco, Town Resaca as higher, and then your water sample tended to not follow that general correlation as compared to the other Resacas. And I'm a avid studier of the Resaca systems. Why do you think Lozano Banco and Town Resaca were overall higher when you add all those three? And what particularly, and you kind of allude to that in your paper and in your presentation about basically urbanization and it's more urbanized, but what specifically as far as mechanism, and if it's in the report and I missed it, that's fine. What mechanism, how do you think the plastic gets into those systems more preferentially? What mechanism physically is going on here? Did you look at that at all, or do you think that that's good for a follow-on study, or can you provide any comments on that?
I definitely do think it's good for a follow-on study. I don't want to avoid that question though. So for this study, I just wanted to find where they were located at. I didn't want to get into say how they were getting there. I think that's good for a follow-up study. But yeah. I think with microplastics, I honestly think they're not really preferential. I think they're just where the pollution is. So I think where it's more urbanized, where there's more pollution present, they're just going to be there. So in Lozano Banco and Town Resaca, I definitely think it's just more likely than somewhere like Rancho Viejo where there's not as many sources.
Yeah. Okay. I bring that up exactly. I don't think it was necessary, and we discussed this, during your proposal. I don't think it was necessary to get into that. But I think with a little bit of additional work from other students that are what other students are doing, I think if a resulting paper from this, one of the things that I'm most curious about is the storm sewer system. And because some of those, particularly Lozano Banco and Town Resaca, are heavily piped systems, meaning there's straight conduits from the street network to those bodies of water, whereas you're not going to see that as frequently in Resaca de la Guerra and Rancho. And so that is interesting. I think the other factor would be the source water into that system. And my second question and last question really right now for when everybody's here is you did not do any, I thought originally we were going to look at Rio Grande and sample there. And I think that kind of fell off maybe as a result of limitations on your work from the pandemic and or time. But how do you think that data, if you did have some samples, what would you expect? And how do you think that impacts your results?
So for the Rio Grande, yeah, we were going to do the Rio Grande originally, but we ended up just hopping on the study with David and them because they already had permits for the Resacas. But for the Rio Grande, I think that I think it'd be very polluted just because of the trash pollution that comes from both Mexico and the U.S. And I'm not sure how much effluent the Rio Grande experiences, but if it does experience stormwater effluent and wastewater effluent, I expect that the microplastics there would be very high. And I think that is a potential study. I think it should be done because one hasn't been done on the Rio Grande in a very long time.
Yeah, I think that would be really. I think that factor is probably the second most potentially impactful factor, in addition to just urban density. So I think urban density, which you hit on, the storm sewer network density, and how much of the area is actually directly fed in. And then, as you alluded to in your report, and I applaud that bit of the work on the Resacas, is that these Resacas are now, basically dislocated from the Rio Grande and are artificially filled with river water, excuse me. And because of that, you're going to have a component. So there could be some simple correlations. If we do get a little bit of data, and I'm not saying this is necessary for your work, follow-on work, I think it would be a great bit to correlate those three factors: urbanization, storm sewer systems, and the river, and see just where potentially we can determine where these plastics are coming from more preferentially, so that we can start to, off this limited but very important data set, start to potentially develop some policy studies and how we might be able to impact or mitigate some of the impact of plastic pollution on real systems. So that's all the questions I have right now. I applaud your work. You did very fast, efficient work during a kind of a tumultuous time. I'll leave it to others on the committee as far as your laboratory methodology and your collection, sample, and statistical analysis. So thank you.
Awesome. Thank you, Dr. Jude. And thank you for bringing that up about the wastewater and sewage effluent. A lot of studies out there right now are studying sewage effluent, and they're finding out how wastewater facilities aren't actually filtering out many of the microfibers. They're just being sent back into the environment. So I think that would be very important to study in the Rio Grande Valley to see if that's a potential source.
Yep. Got it. Thank you.
So you have a question in the chat. Tyler asks, did you publish the FTIR library you created anywhere so other researchers can use it?
That's a very good question. So I haven't published any of my work yet. I've thought about publishing this because whenever I tried to look for a library to use, all of them costs thousands of dollars to download. So I think having a base level introductory plastic polymer, what could be in the environment library, would be a good thing for those who are just getting into microplastics to have. So that's something I'll potentially look into. Thanks for the question.
Okay, more questions.
Yes, this is Carlos Sintra.
Yes.
With Job West, I will agree with people. Just a recommendation regarding the potential publication of the database. If you're looking into publishing your paper, many times you can actually put a data archive within the journal as supplementary material, and that way people can access that. Normally you can negotiate some publication costs if the journal that you're targeting happens to charge for the publication in itself, but that will be one venue. And they should be similar banks like the Gen Bank and the like for you to publish this type of work. But now let's go into my question in here. One of the graphs that you put in your histograms, in which you're showing the frequency of the distribution by the Resacas of either associated with any of the fish or the combination of that. Can you give us a little bit of a perspective of the breakdown of how many fish came from each of the Resacas?
Yeah, I have that in my data. I don't know if I have any graphs here that show the actual sample numbers, but originally we were trying to collect 10 from each Resaca. Some stuff happened with the permit, so we aimed at just collecting 10 from each Resaca system. And some of the Resacas, we would catch more species than other. It was all random. It was all really opportune sampling. So however many we could catch, we wouldn't exceed 10, but it was just, we would catch what we could catch from each Resaca. I know for the Rancho Viejo system, like I said, with the self-fin catfish, we were only able to catch 3. And there were some systems where we were able to catch our limit for gizzard shad and self-fins, and there were some where we could only catch 1 or 0. But I don't have the data with me right this minute. I think it's in my paper though. Yeah,
no problem. Just as a follow-up with that, given what you just said about your limits, and that is just accessibility to the sample based on the technique that you use in the equation, how do you think your data will be looking if you were able to even the samples across the board? So if you had catch 10 individuals of each species at any given pool within each of the Resacas, because right now it seems like probably your results might be hiding some of the overall effects by having a larger concentration in Resaca Lozano compared to Rancho Viejo or even Resaca de la Guerra.
Yeah, I get what you're saying. With Lozano Banco, we only caught 10 gizzard shad and 10 self-fin catfish, so there was only 20 of those. And the other Resacas, they had sometimes 2 to 4 pools apiece. So they usually made up for it with, yeah, they usually made up for it in numbers. But I get what you're saying. I think that if we had more samples, I think it would change the numbers a bit, but I do think we had a good representative sample of how many plastics were coming out of the digestive tracts of each species. But I guess I can't really speak to it because I don't have those sample numbers, but I think that they would be very close.
All right, thank you. The last question I have, so hopefully the public actually warm up for questions. If you can go to your regression slide, please.
Yes.
So you mentioned that there's an expected increase in terms of the concentration of microplastics given the size of the fish. You also mentioned that in this particular case for Dorosoma sepedianum, the larger individual, obviously, it can be considered an outlier. You remove the outlier and actually show that. However, if you see around the 50 grams in there, that's where you have your largest variability associated with your data set. And in here, pretty much you're looking at probably one of the pools, correct? Or are they all Dorosoma sepedianum in this particular graph?
Can you ask that last part one more time? It cut out.
Yeah, as you're looking at the Dorosoma sepedianum, in here you say that's all the pools?
Yes.
Yeah, so does that mean that you only caught 9 fish total?
So
only 9 data points represented in the graph?
Yeah, so these are the average weights and average numbers of microplastics from each pool. So like I said earlier, we didn't catch some species from some pools. So this is for gizzard shad. So there was a pool in the town Resaca system and a pool in the Resaca de la Guerra system where we didn't catch any. So there's only 9 pools out of the 11 here because that's
okay.
The only...
So it's an average. Oh, then that's okay because I don't see the numbers correctly. That's where I'm coming from. So now you clarify that these are averages points plotted, not individual fish.
Yes, I'm glad I could clarify that. Thank you for asking about that.
All right, thank you. That'll be it.
Thank you, Dr. Sindra.
And Carlos, we'll get you a copy of the final thesis so that you can look at those numbers on the numbers of fish in each pool. Okay.
Thanks, Elizabeth.
No problem.
Yes, ma'am. This is John Franklin, Wesley's father. Wesley, you did a great job. Me and your mom was watching. Seemed like you were very knowledgeable. You did a great job presenting the evidence here. And I want to thank your advisor for allowing us to be a part of this and to be able to watch this morning. My question for you is, how can the community be aware of the rise in this microplastic? I know most of the people in your field realizes that this is becoming more and more of a problem, but what can be done to make the community aware of this so that we can be better stewards of taking care of our environment?
Thanks, Dad. That's a really good question. So that's the thing. Scientists are known for being bad at actually getting the stuff they know out into the general public. So we just need to implement this into education, both like in school and also like community outreach. So putting signs out, having seminars, things that will actually engage the general public. Because like you said, if scientists know about it, that's cool. But if the public doesn't know, generally things are going to change. So just education outreach and community outreach.
Sounds good. Thank you.
Thank you.
Somebody else has to have a question.
Right?
Elizabeth, I have a comment, if you don't mind.
Go for it.
Regarding your father's question there, number one, I think it's great that they're participating. I think this is the second time only in my career that I've seen parents have the opportunity to participate and ask questions. And along those lines, I think one of the reasons why Wes's work is so impactful. I'm pretty sure, Ms. Franklin, that you don't, aren't as familiar with Resaca systems. You probably are simply by knowing your son's work than a lot of people are down here. But they are understudied systems, meaning that because they're ancient distributaries and they're no longer connected to the river, And they're very small and local systems, although they are over 300 river miles long when you add them all up. They're an underappreciated environmental resource, but they're also very heavily human managed because we pump that water into those systems. And because of that, the pure naturalist looks at them as a human involved system, and the pure social side on the human management system, we don't have a lot of money down here to manage a system like this all on our own. So studies that come out of some of our students in School of Earth, Environmental, Marine Sciences, like Wes's and others, are really, really important. And probably the most impactful thing is to raise awareness of the Resacas as a whole, and the fact that we, because we are managing the system hydrologically, water-wise, that we have to manage the system ecologically and environmentally. And without that data, we have nothing to stand on. And without students doing the grunt work that Dr. Heiss and Dr. Fierro and myself and Dr. Sintra, I'm going to speak for all four of us, are getting a little longer in the tooth. It relies on younger folks to do the brute force collection and then for us to guide them. So I think it's fantastic that this study happened, and that I encourage fellow colleagues to look at some aspect of Resacas in their work in the future. So thanks for asking that question, Mr. Franklin, and thanks for relating that to what I think in my area is one of the most important issues we have as scientists in this region, is reaching out to this underserved public.
Yes, sir. Thank you. You're welcome.
Okay, anyone else? I want to once again thank Wes for doing such a great job. I am very proud to present the work that you've done and to share it with all these wonderful people. I want to thank all of our guests for attending. It really does help to have an audience, believe it or not. It's really hard to do things over Zoom, and having people here who are interested and engaged and asking questions helps a lot with overcoming the awkwardness of COVID. So appreciate that. I hope everyone stays safe and gets their COVID vaccine when they get the opportunity. And I guess we'll end the public part of this and recess into the committee meeting. Unless anybody's got anything else. You all.